The screen has to be, it's not getting disturbed. All right. Because when you do something, it is getting disturbed. So, all right. All right. So first of all, we'll try to focus on importance of storage systems. We'll also try to understand types of storage systems, battery key terms, types of batteries, battery modeling, cell selection, factors affecting battery, IEEE practices, and finally, IEEE standards. Now, why do we use storage system? Though we discussed enough during past lectures, but when we are talking about importance of storage systems, first of all, during renewable excess of renewable energy, when demand is less, and supply the required deficit power when renewable energy or renewable generation is less. So the storage can be used as a device to observe the excess energy and discharge when the requirement is not met by the energy sources. Now, when you talk about islanded mode of operation, or that is grid support action, which helps to regulate the whenever there is a generator connected to a particular bus, the voltage distributed generators. So the voltage at a particular bus can be regulated by systems. Finally, we can also flatten the load curve. Usage of batteries can flatten the load curve. So how it can be flattened? Because load curve is like a valley. Whenever we have a peak, whenever we have an off peak, I can start charging my batteries. And when we have peak, I can start discharging my batteries. So perhaps through that process, the load curve can be made reasonably flattened. We'll also try to understand a couple of case studies where huge storages are being, deployed across the world. But one of the 100 megawatt battery installed by Tesla in South Australia happened to be an example of master that the Elon Musk, now he's very popular. But at that time, he was just a Tesla man, okay? And within 30 days, within 100 days, 3 months, within 100 days, close to 3 months, 100 megawatt battery installed by Tesla in South Australia. So this is one of the strongest example for all of us that if required, amount of across the world, across the country. So Southern Australia has been crippled by electricity problem uh, in the past, even today. So peak demand occurred due to local hot weather. So they experience a huge peak, and though they don't know what to do. So curtailment, energy curtailment in Western country or developing nation become a question because that electricity is an excess, which is the right excess. You famously worked to build the battery within 100 days. And this is the history in the making. That means such kind of installation has never happened in the history of this world today. So this is one of the interesting example. I thought of sharing it. Now, there are many non-electric storage systems, though they do exist. First one is actually mechanical storage type. There are many types, pump, water storage, compressed electrochemical storage type, accumulators with internal storage, accumulator with external storage, hydrogen system, and water. Now, electric storage, we call it a supercapacitor, is another storage systems, and superconducting energy storage is also one of the variety. It improves the reliability of the utility or customers. It helps in achieving power balance by charging and discharging. It also reduces the system losses and improves overall efficiency. How does it reduce the losses? Any one of you can just imagine, because when you have a battery, because it is locally connected, okay, so it is normally do not flow, the energy from the battery do not flow a long distance, okay, so that is why we say the energy you have produced, preserved, and delivered almost in a reasonably closer environment, very short duration, short distance travel. So we reduce the losses and improve overall efficiency of the system. It reduces, there is peak energy. I think we cannot depend on any rotating machine devices like thermal power plants cannot come to action. So we have to go either to diesel generators or storages. I think diesel generator is not a good option. So to me and to all of you, I think battery is one of the best solution to make the system resilient. Provides ancillary services like fault right through. Now, what are the key deciding factors when you go for battery storage systems? How do you decide whether to go for battery storage system or not? Should match with the properties of the power system. Should match with the properties of the power systems. Required storage capacity, minimum storage period, charging and discharging time, because these are the variables will decide what type, how much, where, when, through the information available to you related to energy density and lifetime, available location and environmental factors, minimum number of storage cycles. So these are the key deciding factors for your energy storage systems. Now there are a few terminologies that we need to understand. For example, battery duty cycle. We keep on reading, so this next 2-3 minutes is quite important. The sequence of loads a battery is battery duty cycle. We frequently use the term cell size. Okay, rated capacity of a cell or the number of positive plates in a cell. Correct iniquities of voltages, specific gravity or state of charge. One more important point, which is full float operation. Full float operation, that is the operation of a DC system on float charge with infrequent discharges. Okay, so it is in the floating state. Okay, period means an interval of time in the battery duty cycle during which the current is assumed yeah, I think yes. Sorry, there is some small change here. Yes, period means an interval of time in the battery duty cycle during which the current is assumed to be constant for purposes of cell sizing calculations. We also talk about rated capacity. For example, in lead acid cell, the capacity assigned to a cell by its manufacturer for a given discharge rate at a specified electrolyte temperature and specific gravity. Very important. If you really like to spend some good time on storage and if you're really doing some good research, then those basics are actually very, very important. Otherwise, you cannot model any battery properly. So then we talk about vented battery. What is vented battery? A battery in which the products of electrolysis and evaporation are allowed to escape to the atmosphere as they are generated. So these batteries are also commonly referred, which is very commonly used. I know 99% of you must be knowing about SOC, but today we'll talk about SOC and DOD, how they are similar and how they are dissimilar also. State of charge, SOC, using the analogy of a fuel tank in a car, a state of oil, state of gas, similarly state of charge of the battery. So how much energy is there in your batteries terminal? I mean, the terminology for that is of SOC. Okay. You put a scale and measure how much oil is there. So similarly, SOC gives an idea, measuring and telling you how much battery capacity is still available to you. So SOC or depth of discharge. So they are not equal, but they're extremely closely related. That's what we are saying, SOC or depth of discharge. SOC is different, DOD is different. Their SOC will be 1 minus DOD, we'll see slowly. Can be determined by measuring the voltages. Once again, I like to repeat that percent means the SOC is going to be, and the depth of discharge is going to be 25%. So one, now we'll get into different types of batteries. Lead acid batteries suitable for large storage application. Sodium, very popular, NAS. High energy density, 4 times of the lead acid, suitable for microgrid applications. Long cycle capability. We have one more category known as nickel cadmium. Cadmium toxicity costlier. Applications include cordless telephones, emergency lighting, etc. And then we'll slowly move to just a minute, sorry. Nickel metal hydrate, which is low internal resistance and suitable for high current drain applications. Applications include digital cameras and high drain devices and also environmentally friendly, suitable for portable devices like mobile, laptop, and also electric vehicles. These batteries, other lithium batteries, electrically used in applications where weight is a critical feature, suitable for portable devices like mobile phones and notebook computers. And we can also get into battery modeling with key terminologies. To quantify the behavior of a battery, different parameters are studied, among which state of charge, SOC, capacity, C, and depth of discharge, DOD, which defines the dynamics of a battery. So you must know what is capacity, what is SOC, and what is DOD. Compared with the energy it had when it was fully given an indication of how much longer a battery will continue to serve before it needs recharging. This defines as the available capacity expressed as a percentage of some reference. Sometimes it is rated capacity, but more likely its current capacity, that is at the latest charge discharge cycle. SOC is 100% when fully charged, and SOC becomes 0% when it is fully discharged. That means the battery capacity C measured in ampere hour or milliampere hour. Ampere hour or milliampere hour represent the maximum amount of energy that can be extracted from the battery under certain specific conditions. In many type of batteries, the full energy stored in the battery cannot be withdrawn. In other words, the battery cannot be fully discharged without causing serious and often irreparable damage to the battery. So that means there are many technologies in which you cannot make it zero. If it is there with some 10-20%. So is discharged. When a battery is 100% full, the DOD is expressed as a percentage of rated capacity. For example, if 25 ampere hour depth of discharge is 25% and the battery is at a 75% state of charge, such that the depth of discharge is 1 minus SOC in terms of percentage. Now we can slowly get into battery modeling, as we have already seen in the past. So this is a very simple battery equivalent circuit, and we can determine the SOC, which is the previous SOC plus 1 upon C integral IDT will give you the current SOC. Type of magnetic energy storages, superconducting magnetic energy storages. What is this operation and feature? What are the issues and applications we'll discuss with different type of storage technologies. So SMES employs the storage of energy in the magnetic field around the coil carrying a DC current. Employment of coils made of superconducting materials is necessary in order to reduce the energy losses. What are the issues? The manufacturing practices and cooling practices. Even a small AC component of SMEs, automatic generation control, spinning reserve. It can also be used for subsynchronous resonance damping. We'll move to supercapacitor, which is a very popular component in powertronics, field of powertronics. So supercapacitor and ultracapacitors. The operation and features, operation is similar to traditional capacitors. However, its capacity and discharge current is much higher. Easier to obtain state of charge is that of secondary batteries. Issues mainly because of specific energy of ACs is lower than that of traditional secondary batteries. Cell module voltage imbalance is very common. Now in DC microgrid, to compensate for high switching transient, DFIG fault right through improvement also capacitor, the way we model battery. One can ask actually, can you model the supercapacitor? So probably students must be very careful. Maybe let's say Manmohan is very keen to ask a question. Please choose which model is representing supercapacitor. So this is how it looks like supercapacitor mathematical modeling. And the right side very clearly talks about the modeling equations. It's a very simple, RCN series in shunt with resistance. And we can create some modeling equations for supercapacitor. Consider the cell and what are the factors need to be considered. Physical characteristics such as dimensions and weight of the cell, container materials, planned life of the installation and expected service life of the cell, frequency and depth of discharge, ambient temperature. Note the sustained high ambient temperature result in reduced battery life. You can refer to different IEEE standards. Charging characteristics, maintain seismic characteristics, and spill management. Now, okay, so if F is my cell size, and that need to be optimized by maximizing f of s from s varies from 1 to n, and where all the variables such as the section of the duty cycle being analyzed, number of periods of duty cycle, P is the period being analyzed, AP is the amperes required for the period P, T is the time in minutes from the beginning and period P through the end of section 5. CT is the capacity rating factor for a given cell type at the T minutes discharge rate. Fs is the capacity required by each section. So it's a very simple equation. If you are interested to work on optimizing the cell sizing, probably this equation can be used. So key factors governing the size of the battery: system voltage, minimum system voltage, and correction factors. These are the four important factors that decides the size. You say this is a good battery, that is a bad battery. First is voltage level. When a cell or a battery is discharged, its voltage is lower than the theoretical voltage. State of charge: as the current drain of the battery is increased, the service life of the battery is also reduced. Mode of discharge depends on constant resistance, constant current, as well as constant power. Factors affecting battery performance is mainly due to temperature of the battery. Lowering of the discharge temperature will result in a reduction of its capacity. At higher temperature, the internal resistance decreases. And energy output usually increases as well. But discharge current decreases with the hours of the service. So the service life depends on discharge current. Now, type of discharge, if I talk about type of discharge, depends on continuous or intermittent discharge. As I told you once during my discussion, normally we have to avoid, intermittent way of charging and discharging. The voltage regulation of the equipment influence the capacity of service life of the battery. If a rechargeable battery is used with another permanently connected source, battery equipment should tolerate the voltage of the battery on charge. That is charging voltage strength. Then we'll talk about battery age and storage condition. Batteries are, perishable product and depends on cell packaging techniques, spacing between the cells, container material, insulation, potting compound, fuses, and other electronic controls also affect the design, depends on the life of a battery. Depends on the load, where the short pulse loads draws more power than that of a long-term pulse loads. That is my duty cycle. There's practice for sizing lead-acid batteries. How many number of cells, temperature correction factor, design margin, aging factor, initial capacity, for any given stationary applications. Okay, and there are many IEEE recommended standards, and that we need to understand. I recommend all of you to have a look, and each IEEE standard defines the role under this scripture. Okay, so application and management of getting to IEEE P1660 TM. Similarly, IEEE standard for qualifying Class 1 equipment for nuclear lead storage batteries for nuclear power stations, because these are the batteries are being used. What with the temperature, whatever the voltage, whatever the duty cycle. So I recommend strongly all of you, because I given you just standards in detail to appreciate what exactly and what are the recommendations by the IEEE for specific applications. I think most of you never thought that I will also provide you the IEEE standards for your level to capture this. But I thought when you talk about storage, we started from very fundamental yesterday's lecture and today's lecture along with IEEE standards. I think now you are enough to do some good job. At least one chapter in your thesis or MTech dissertation is possible on storage now. With this note, we complete storage here. And we'll also move to the next section, which is fundamentals of smart grid operation and control of AC microgrid part 1. Yesterday, we have gone through now we'll be trying to cover actually there are a few challenges with AC microgrid because AC microgrid operate with different modes, general mode or islanded mode. We'll also understand what is the meaning of islanding of microgrids and then control of distributed generations with microgrids. What type of control mechanisms are microgrid ancillary services? One case study we'll try to cover today. So this is my AC microgrid, and then in case of a DC, I have shown you, if you have a DC grid, all the type of injections from different cells, storages, generations, and the loads are also for DC type. But this is a typical AC microgrid, and to me, AC microgrid is more popular because if you have AC microgrid, so from the diagram, you can all see that we have, fuel cells, batteries, isn't it? Battery sources in AC grid. And then you have different loads like energy coming from actually PV as well as wind turbine connected to AC grid. And then you have consumers like electric vehicles and other type of load. Of common coupling, which is connected to my regular AC grid. So a microgrid, AC microgrid is connected to my AC grid through a point of common coupling. And within the microgrid, so many actions will take place based on the its operation and mechanism of integration. So microgrid, someone asked me what is microgrid? What is megagrid? What is so many why not nanogrid? Isn't it? So anyone can answer? Why don't we call it as a nanogrid? Why we call it as a microgrid? Just to message in your message box. Can we replace microgrid by nanogrid? To me, it is yes. Anything because it has been told to us microgrid, so we are very particular. But if I say it is a nanogrid, why micro? Nobody knows. Am I right? Nanogrid. No clue. Okay. Ah. No worry. Actually, I will try to help you slowly. Don't worry. So, you see, microgrid is basically initial breakthrough thought process. I will come to that point slowly. Microgrid is a localized group of electricity sources and loads that normally operates connected to and synchronous with a traditional centralized electrical grid called as microgrid, but can also disconnect to island mode and function autonomously as per physically as well as for economic conditions. So typical structure is given to you. Microgrids are small electrical distribution systems that connect multiple customers to multiple distributed source of generation. I will try to help you now. In Indian context, actually, what is micro? Installation capacity, which is close to 500 megawatt, gigawatt, sorry, 500 gigawatt. And if I, because this is grid now, the grid is 500 gigawatt. Now, if I say microgrid, that means reduced by 10 to power 6 times. That is my actually microgrid. Am I right? So, if I multiply gigawatt to 6, 10 to power 9. Am I right? 500 giga multiplied by 10 to the power minus 6 will be how much? Okay, so this is basically 500 kilowatt or half a megawatt. Okay, so reasonably, a system of 1 megawatt scale can be, I can say a 10 megawatt can be considered as a microgrid, isn't it? So reasonable 10 megawatt can be popularly known as microgrid. I mean, now consider 10 megawatt multiplied by 10 to the power minus 6. 1,000 watt could be a nanogrid. Are you clear? So there is, don't go with my electric grid and the range of microgrid. What I will call? Will I call Jaipur city as a microgrid, or Amenity campus as a microgrid, or Acharya Bhavan staff colony as a microgrid, or which is not a, which is a nanogrid and which is a picogrid. Okay, so I hope you have enjoyed with this because this is not written in textbooks. It is just my personal guess, but it is working very well with the definitions. Have you understood? Please say message. Any doubt? Any more clarifications? Anyone? Oh, they understood. Rahul understood. Yes, yes, yes. I think this is how there is no standard definition, but you and then nano and pico is further smaller actually. But what is the range and which one is micro? For example, if you go to Andaman Nicobar or if you go to Arunachal Pradesh, the Arunachal Pradesh grid become a microgrid to me sometimes because only 10 houses become a district. You come to Mumbai where the weights and the gravity of the problem. So you can just popularly understand how to design a microgrid, what is its capacity, which is called microgrid. Is it a microgrid application suitable for this or not? Can be easily understood. No worry. So now moving back to the regular understanding of microgrid, AC microgrid. Today we are talking about AC microgrid operation modes. One is grid connected mode, and the second one is islanding mode. So grid connecting mode, it is a normal operation. Distribution grid being either partially supplied from it or injecting some amount of power into it. Okay. Power reference for the microgrid control, very important now. Each and every word that I'm going to spell from now till next 15 minutes is very, very important. Power references for the microgrid control are issued by the microgrid centralized control, so-called MGCC, microgrid centralized controller. The generations, okay, that is microcontrollers, is known as is said to be in PQ mode. Okay, DG is said to be in PQ mode actually. The terminology slightly differs. The microgrid islanding process may result from a or our state electricity authorities do it during emergency from the due to maintenance needs also sometimes due to energy shortages or from a forced disconnection due to a fault in the medium voltage network such as voltage dips. If there is some problem, there is a transformer blast and then they disconnect you from the main grid. So in islanded mode, one distributed generation, one DG may be operated in the VF mode and the others in the PQ mode. The control system in the local controller of the distributed DGs is known as PQ inverter control, and the DG is said to be. Now, what is islanding? Because that's a very important question. Islanding is a critical and unsafe condition in which a distributed generator, such as solar system, continues to supply power to the grid while the electric utility is down. I will tell you one very interesting example. During 2012, I happened to be, I normally frequently travel to US at least once in a year for general meeting. So 2012, I was in US for a meeting. Now, India is the only country as of now which has never experienced a blackout. The United States have faced multiple blackouts. So I was a bit proud and privileged to say always the transmission grid is very good. Difference we don't electricity, and we have been told that for a couple of architecture. And then prior to my departure, we have installed 1.73 megawatt of PV panels for helping the implementation process. So I said just now before departure, I have, as a team, we have installed 1.73 megawatt of PV. And now you are saying there is no electricity. How it can happen? And to be very honest, I could not connect what exactly went wrong. I said, even the bulb is not glowing. She said, no, nothing is happening. So then I said, all my 1.73 megawatt of PV that I have connected is now sitting redundant because the fault happened somewhere in Uttar Pradesh. But what happened to my DC grid, which is just sitting in the rooftop? Am I right? At the time when I landed in India, we learned that actually the importance of island. Having our own resources, still we are not able to survive very quickly because when through diesel generate anyway we can manage. I'm not worried about that. But when the grid is not there, even your renewable energy stop, especially PV stop generating, am I right? Because there is no reference voltage point for that. So that's why. What is islanding? Islanding is a critical and unsafe condition in which a distributed generator, such as solar system, on that day of hydrology, the story that while the electric utility is down. That means will still continue to produce their generations, even we can say this island in of operation. Otherwise, it's a blackout. Am I right? So, damage to customers' appliances due to voltage fluctuation. Inverter damage leads to malfunctioning of inverters. constantly communicating between the distributed generators and the grid to ensure the status of electric supply. Passive islanding may. So one more interesting thing here, when the grid is disconnected, if we as well as disconnecting as and when desired. Let's say there is a fault, I must be in a position to disconnect, in a position to connect it also, isn't it? So for that, you need a strong control mechanism. And long time instead of getting connected quickly. So there are different type of control schemes in distributed generation. They are actually control of synchronous generators, control of inverter-based DGs, and control of inverter-based DGs are again divided. Grid connected mode is grid feeding strategy or grid supporting strategy. And islanding mode, actually, they are either grid forming, grid feeding, or grid support. I think by this time, hopefully, you know, the so when the how actually the mechanism for control during grid forming, what happens, grid feeding, what happens, and grid support, actually what happens. So in one case, actually, it is when you say it is grid feeding or grid forming, in one case it is acting like a current source, the other case it is acting like a voltage source, and the third case actually it is a combination either current or voltage source. I'll be teaching you very soon for detailed discussions. So before we get into that, let us quickly understand about control of synchronous based generator based distributed generations. Microgrids are powered by single AC generator or gas turbine. It's regulated in response to the load changes, which would tend to cause changes in the speed. So this is a very. Now, if I talk about inverter-based distributed generations, so due to internal characteristic, most distributed generations are not suitable for direct connection to an electrical networks. Therefore, power electronics interface are required. The most conventional power electronics topology is the back-to-back structure with two VSCs, one for the generator side converter and one for the grid side converter. The generator side converter are usually controlled to implement a maximum power point tracking, that is MPPT, and the grid side converter is usually three-phase. Inputs are supplied by the grid, so all dispatches, distributed generators, inverters must be controlled. Now, if I classify the power converters in a microgrid, as I told you, what is grid feeding? I think I need your attention for next 5 minutes now. Grid feeding, that is also known as actually grid following. Grid feeding power converters are mainly designed to deliver power to an energized grid. They can be represented by an ideal current source connected to the grid in parallel with a high impedance. These power converters are suitable to operate in parallel with other grid feeding power converters in grid connected. These converters participate in the control of the microgrid AC voltage amplitude, references of active and reactive power P and Q to be delivered. Grid feeding power converters, grid forming or grid supporting power converters, or a local synchronous generator setting the voltage amplitude and frequency of the AC microgrid. All right. So now we'll move slowly to grid forming. The grid forming converters can be represented as an ideal AC as voltage, because it's grid forming, okay? So we are considering it's a voltage source, its own. They need an extremely accurate synchronization system to operate in parallel with other grid forming converters. For example, 10 UPS. In a microgrid, the AC voltage generated by the grid forming power converter will be used as a suitable for islanding operation. So grid feeding is basically, and grid supporting will be, the grid supporting converters can be represented either as with a shunt impedance or as an or ideal voltage source in series with a link impedance. Its main objective is to participate in the regulation of the AC grid voltage amplitude E and frequency omega by controlling the active and reactive power delivered to the grid. This kind of converters can participate in regulating the amplitude and the frequency of the grid voltage in both grid connected and islanded microgrid. An example of grid supporting power converters can be found in line. So grid feeding strategy, they are actually passive generators mostly. And you can see that, you have a PV panel with a grid feeding strategy using a choke filter. The grid side converter GSC is controlled as a current control capability. Power transformation is used for extracting DQ excess of current components. The real power is controlled through D components of current by regulating DC link voltage. The reactive power is controlled through Q component of the current. Now, similarly, if you go for grid feeding strategy for PQ mode for renewable energy sources such as, okay, in the distributed generation with the possibility of increasing or decreasing the amount of primary power, an additional active power reference can be used by the local controller MGCC. There is a message which is coming. Okay, I think we'll, at this point of time, no, but we'll get into details of part transfer. One more, please take a note. So perhaps actually what we'll do, we will provide you, because I think some materials, some study materials actually can be shared. So what we'll do today, tonight, we'll share ABC to DQ, DQ to ABC, that can be shared. We'll do that today. Okay. So Dr. will share a public domain. Okay. So that you can all read it. This kind of DGs are dispatchable, and their control system is known as PQ control. Now, if you go for inverter control in islanded mode, uh, what is inverter control in islanded mode? So DG must feed the microgrid with predefined values for the system voltage and frequency variables. So in order to generate AC voltage, AC capacitors are required. So LCL filters are used. At least one DG must. To give you some bit of introduction to different mathematical equations, inverter control in islanded mode. You can see a single phase equivalent circuit, okay, the vector diagram, and then you can determine the powers at the capacitor connected side. Okay, so the PG and QG will be of the certain equations. Moving to islanded control in islanded mode, the basic control scheme in three-phase grid forming mode. All right, so they are and then we will just also get into ancillary service application. We talk about grid connected mode, that is the normal operation. They can certainly support your frequency. They can support your grid loss. They can support your voltages. They can support your congestion, and improvement of power quality is also possible. However, in case of islanding mode, actually, it can help you to go for black start and also grid forming operation, that is frequency control and voltage control is possible. So microgrid is an asset, not only giving why we go for microgrid. Microgrid also play an important role to provide ancillary services because they have enough to help the main grid. Okay, so the main idea is to give electricity access to everyone in the country, and we move to microgrid. Probably isolate island mode of operation is also possible. Certain challenges in transmission system, but they also indirectly help the major system, main system in some of the situations. So support, how does it support frequency? Let us understand. So you could see the right hand side, we have a distribution network and we have a microgrid in place. We have distribution network. Let's see how the frequency behavior can change because of the microgrid. In order to describe the capability to the provision of ancillary services, frequency regulation support, he study is illustrated. Okay, for the distributed network owner, what is distributed network owner? Distributed network owner means a company or a body that looks after the distribution system. An interconnected microgrid can be considered as a potential power reserve contributor because distribution network owner has actually a lot of things and they have a lot of sources, a lot of microgrids, a lot of distributed generators. For example, if I say we are actually 140 crore people, divide by 5 on an average, so which is going to be 30 crore houses, and each one of them, if alternate house has a UPS in the past, okay, now the fluctuation of electricity reduced, but previously, immediately before a car, they will buy a UPS actually. So a lead acid battery being stored, okay. So alternate, if you say, so that means 15, crore batteries. Kilowatt, even 2 kilowatt, even 1 kilowatt. That means 15 into 10 to the power 150 megawatt, isn't it? So almost 150 megawatt of capacity sitting ideal all the time. Could you imagine? So if I say all the, if you in the message, if there is a mobile, if I say, come on, switch on your EPS, any peak can easily be resolved. Are you getting the point? So that is what the frequency support of the system is all about. So these microgrids can help that, an advanced interface control system inside the microgrid control must be developed in order to provide the available regulation power in compliance. Instead of getting into a mobile information to operate, we can have an automated system when to react and when to not react. In order to provide the available regulation power in compliance with the distribution network requirements. The block of ancillary services implements the grid integration and coordination of the microgrid with the main grid. That is so coordination today people call transmission system operator, distribution system operator. They have to coordinate and exchange information. Transfer. So when the frequency, deviation exceeds a predefined threshold value, very important, the primary frequency control will be activated to increase or decrease the power from the prime mover to restore the power balance. All right. If the frequency changes from F reference to F1, the reference of the generator power will move in normal conditions from PMG reference to another PMG reference 1. After restoration of the power balance by the primary control, the system is stable, point number 2, but another frequency F1. The secondary frequency control brings the point is changed to point number 3. So that is how actually the PF characteristic or PF curve, I mean, we now PF characteristic of any grid or a machine will be able to understand more in detail. So for the given application, the DNO sends a wished dispatching system control power reference signal that will be given by the DNO, which is known as PMG DNO reference, which is considered as a how much power the conventional power or frequency control principle can also be used inside the microgrid control in order to create the microgrid contribution to the main grid primary frequency control. So if you have 1,000 microgrids or can play an important role in your primary frequency control of the whole system. All right, so this is microgrid and microgrid ancillary services, another case study, a microgrid case supporting the main grid frequency regulation. And power dispatching, a case study system. So now we'll talk about little bit on power dispatching, which is a power management. The three distributed generators, PV, we can see that we have a PV system, gas microturbine, and supercapacitors to supply local loads in an optimal way for the electrical distribution and production. So what we are thinking, Manmohan, that we are talking about there is a combination of different sources, photovoltaic, all three together like to cater a load. So the power dispatching is based on a power management X amount, how much I have to take from this fellow, that fellow, and that fellow, right? Before sending the dispatching power set point to each unit, for the given case study, the balancing condition implies that the exchange power with the distribution network has to be produced from all sources in the microgrid. So we say that P microgrid is my PMT plus PPV plus PSC and PCP. So what is MG is the total power of the microgrid. PMT is the power from the microturbine. PPV is the power from the PV. PSC is the power from the supercapacitor. And PCP is the total consumed power by the local. So I have to generate something which will be equal to load plus the other local sources. Am I right? So total power of the microgrid is the power generation. So normally when you define a system, system power we define based on the rating of each devices. Now since the microturbine has a slow dynamic response time, the power management strategy used to provide the power for a long time range and to ensure the long-term energy management. So depending upon the transient, what time, how fast, how quick, have the dynamic ability to master the real-time fast variations of the power flow, and here they're used to ensure the short-term power balancing. So supercapacitors have a finite storage capacity. They cannot be so big. The terminal voltage of the supercapacitor represents its energy storage level. For security reason, it should be between the maximum allowed value, which represents the maximum storage energy, that is ESC, energy of supercapacitor maximum, and 50% of the value, which represents the minimum storage reconciliation. In order to limit the terminal voltage, an additional control function has to be used. So to lecture is majorly on, we started with storage technologies, different technology for storage, then we moved to AC micro. Get into the control mechanisms, grid forming, grid feeding, am I right? Grid support mode of operation. And then we slowly realize what are the kind of applications a microgrid can play. Okay, so microgrid is not a liability, but it complements to the existing power system. So with this note, we come to an end today. Thank you very much for your wonderful attention and patient hearing. And if you have any questions in mind, please do not hesitate to ask.
Thank you very much for delivering nice talk on control of AC microgrids and before that on storage devices. So now the desk is open to ask any questions if you have. So we are making you panelist. You can unmute yourself and ask a question from self, or you may type whatever you feel better.
I have this all of you. I think now we are truly into the course. Okay. So next day onwards, actually, the lecture 4, 5, everything is important. But what I wanted to say, the joy of understanding microgrid begins now. And probably we'll get into deeper and deeper actually. Yeah. Due to sort of time, actually, sometime I went a little fast. But what I suggest strongly that even though you are not hesitant, because they are not able to ask questions very quickly because they have not really completely grasped. So my suggestion will be like, let them go through the material tonight, and then share the questions to. I think you can share any question to Dr. Manu,
Yes, please.
and probably all the doubts will be cleared.
Yes,
And
so
someone asking, yeah, yeah. Okay. So I think we can request everyone to mail any question or clarification. They can answer.
Yes, if you don't have any question now, we will upload the DeFi material today and you read it. And if you have any question, you can send me. So before starting of the lecture, after lecture, next day, we will answer your questions of previous time.
Sure, sure.
So that we can do. So if you don't have any question, then we stop today's lecture here and we'll meet tomorrow. Tomorrow, I'll update the time. There may be some change in time. I'll update you. Okay, so please keep checking WhatsApp and I'll update over there. Thank you.